We've done all that. So that was what I was telling. We need to work in the entire space. So these are the items. Receive side scaling, receive side coalescing, dynamic virtual machine queues, single root I/O virtualization, NIC teaming, RDMA and multichannel, very important. And keep something in mind about receive side scaling for NIC teaming and RDMA. And we have some other stuff, but I'll see where I get today. So, RSS exists for a long time. You've used this. Everybody is using it. You can't buy a server-grade NIC that doesn't use it. But it has a limitation. It takes away the pain of one CPU, one core dealing with all the network I/O, but it only works per connection. And there's the limit. So we'll get back to that later. But there's some new features in there as well. One, it's now NUMA-aware, which is very important on the very large-scale hosts. It can also deal with K groups. Basically, a Windows OS can only deal with 64 processors. So if you have more, you have multiple groups of 64. You need to be able to deal with that. And RSS wasn't. Now it is. And of course, now it also works for UDP traffic, where in the past it didn't. So basically, what do we want to avoid with that? Well, one little processor of a 40 CPU machine has to deal with all the network traffic. So that's what we avoid with our receive side scaling. What's receive segment coalescing? That's something in the NIC. The NIC can actually create one large package from multiple packets coming in within a single interrupt from a single connection, which means that it can, let's say, deal with that package, and that package only has one header. And dealing with the headers in a network package is one of the things that has the most overhead in the network. So this reduces it with 10 to 30%. And if you look at everything that's going to be discussed here, if you count it all up, it amounts to a significant improvement. So where are we at?
Just where it is. Space.
Space? Okay. Something. Yeah, there. Then we'll jump to dynamic virtual machine queue. You all know VMQ probably. It's used in VMware, HyperV. The problem with it didn't scale very well. There's a limited amount of queues. And the queues were handed out in a first come, first serve basis. So if your first 4 machines got a queue and they don't need it, they never give it back. In Windows Server 12, it's dynamic. They can even lose a queue if they're not using it enough. Idle virtual machines will get their queue taken away and handed to one that can use it. So that's a vast improvement. It's now entirely dynamic. Then there's the single root virtualization, which is quite nice. Most NICs support that. You won't even have to change your hardware for this one. Basically, normally, a virtual machine talks to a physical NIC over a virtual switch. That works fine. It's very intelligent. You can do a lot of fun things with it. But it's not the best for extreme low latency, extreme high throughput, extreme performance. So what you want to do there is actually just this. You have a network card that has a virtual function. That virtual function gets a virtual driver and connects the virtual machine straight up to the hardware, bypassing the virtual switch. This is very performant. But it has one drawback. All the intelligence that vendors build into the hypervisor virtual switch is bypassed. So that's something you have to take into account. And then what's very nice about it, it reduces CPU load, it's low latency, high throughput, it's all very nice. And this is the big killer. It supports live migration, which other vendors don't. You can live migrate a host from a virtual machine, from a host that has SRIUV to another host that doesn't even have a SRIUV capable card. And the way of doing that, I'll skip on the requirements, is actually that's how it works. That's the same picture you've seen before. But now during live migration, it will just switch the traffic back to the software switch from the hypervisor. And whilst it migrates it, it runs in the software switch. When it detects that it has an SRIV card that's capable of dealing with it, it hands it back over. And that's how you are capable of live migrating, or the vMotion in the Windows Server, to use SRIV and still don't lose your virtual machine mobility, which is very important. Most customers don't want to lose functionality to gain something. So it's very important to have this nice features. So this is also nice. You can mix NIC vendors. There's no reason that you can't migrate from an Intel network card host to a Broadcom network card host. It just works. Reliability, I'm going to pass on this one very fast. Basically, this comes down to NIC teaming. You all know NIC teaming. You all want NIC teaming. You all know the hell that NIC teaming can give us. If it works, it's brilliant. If it doesn't work, there's too many factors involved, too many people. So nobody likes it. Everybody wants to get rid of the current system. Well, we've got it. It's finally in Windows. A little applause, 10 years too late, but it's there. You all know what it is. You all know how it works. So basically, what's a very nice one to take into consideration. Some of the advanced network features are not exposed if you team the NICs. So let's say the SRIUV, the single root I/O virtualization. If you want to use that with redundancy, you'll need to do the NIC teaming in the guest. You just take 2 SRIUV cards, create 2 switches, create 2 virtual NICs in every guest, connect them to the different switches, and NIC team in the guest. This is why NIC teaming in a virtual machine itself can be very valuable, because you have redundancy even if advanced features cannot be exposed on top of a physical NIC team. And also for this kind of fancy stuff. This is the old way of virtualizing networks. This is the new way, or one of the new ways. You can actually create a NIC team up to 32 network cards, and you can put all the traffic from the entire cluster over the virtual switch. It's all quality of service, it's all configurable with PowerShell, and you can create a unified network for every type of data you want. And you can tag it, so you can have quality of service, quality of bandwidth, and it's very easy to manage that way. You just put in as many ports as you want or need, or can afford, and you just divide it up. You don't need anything else but the network cards and Windows. So that's what nice. Remote RDMA, that's good. Basically, what is it? How much time do you actually have?
Go 25 minutes still.
Oh, that's good. I don't need to rush at all. I'm going to keep it very simple. RDMA offloads the copying of the data to the network card. And it does it from kernel to kernel. It bypasses the TCP/IP stack in the host. And the best numbers I've seen with Fusion I/O cards as storage copying data was 2.1, 2.4 gigabytes per second. If you use InfiniBand, you would get up to 5.2, 5.3. That means you're copying a DVD per second. So that's awesome throughput. Now you can say, who needs this? Well, you have some new stuff in Windows as well. You can use this to create file shares and put all your virtual machines on there, or your SQL servers. You have a network file system for Windows now. And if you put that in there to talk to your share, you won't have any problems with latency. This outperforms this outperforms Fiber Channel, at least if you're on 4 or 8 gigabit Fiber Channel today. And it's not only that, there's something else. It's called Multichannel. And now you have to remember what I told you about receive side scaling. It only works for a connection. One connection, that's one CPU. Now with Multichannel, that's no longer true. One connection with a RDMA multi-channel capable OS and a capable network card, meaning RSS, it can give multiple processors in multiple channels to one connection. So basically, the first picture is the normal situation you know for RSS. Now if you have multi-channel, now even one connection is spread out across multiple CPUs. So now we're talking. You can do this with as many NICs as you want. So if you have a NIC that's capable of RSS and another NIC that's capable of RSS, another NIC that's capable of RSS, you have multi-channeling across multiple NICs. And multi-channeling is fault tolerant. It can automatically add or lose NICs, but the connection will not be dropped. It will just use less channels. That's also very nice. You can combine this with NIC teaming. NIC teaming can also be enhanced by having NICs that support RSS in combination with multi-channel. Now you have multiple channels per connection, and not just one going to one NIC and the other connection going to the second NIC. You have multiple connections within a NIC or across NICs in a team. And it even handles NIC teams built with different vendors, but also with different receive side scaling capabilities. If you have 16 queues in one and only 8 queues in one, never mind, we'll create one big pool of 24. If you lose the one with the 16, okay, you're down to 8, or vice versa. So it's quite flexible. And then, This is a big killer, of course. If you combine multi-channel with RDMA, you can only describe it as something, the biggest pipes you can imagine for plain 10 gigabit. That's why you get the 2 or the 2.2 gigabytes per second from. Multiple RDMA cards that have multiple channels. And they do the copying kernel to kernel, so it's very fast. There's a little table, you can look at it at the slides later on. It just gives you an idea of what combination can give you the best redundancy with the best performance. And as you might expect, the multiple mix with RDMA are on top. Now, what can I use this for? Well, one use case is, we've been talking about using a file share for storage for your virtual machines or your SQL servers. Well, this is how you get all the throughput needed for that. You put it on an RDMA card with multiple channels. This, I don't have time, so I'm going to skip this. You can have DHCP and router guard protection, so nobody on your network can deploy a DHCP service, or they can, but it's ignored. You can have port mirroring for auditing, so that's also very nice. But then there are some more features. One of them is the data center TCP, and this is very nice. What it actually does is it makes sure that even on cheap switches with low buffer, you can have a very good throughput, very low latency, and you don't have the jigsaw pattern you see there. What you're actually seeing there is a buffer switch being filled at capacity. Then it can't take any more packets. It starts again, it stops again, it starts again, it stops again. The only way to mitigate this today is actually buying very expensive switches with large buffers. They will happily sell you those, but they are very expensive. So if you can manage this, that you get rid of all this stopping and starting and buffer overruns, you get a much smoother experience. And that's what Windows can do now. And basically, I'm going to go to the picture, because this is it. This is where you are today on your networks with your ordinary switches. You have too many cars trying to get in two little buffers between the different hubs, and the hubs are the traffic lights. And to make things even more complex, the traffic lights go from yellow, red, so you stop, you start, you stop, you start, the buffer is full, you end up in your car between buffers. I mean, this is a mess. It doesn't flow very nicely. So what actually Data Center TCP does with Windows Server 2012 is this. It creates a green wave, like in a car. But you need something for that, and that's the traffic center to control everything. And Windows now makes use of what they call the explicit congestion notification. And that's built into just about any modern switch today. Nobody uses it. But that combination of the new OS with that notification gives you traffic control, and you can create a green wave. Your packets just can flow through very easily. It's not reactive anymore. Oh, I can't push a packet in, I have to stop. No, they just stagger it. They manage the traffic going in to ensure a smooth transition of the packet. Then there's data center bridging. Basically, this is quality of service. This allows you to tag your packets and say this packet is so important that it has to go through at that required amount of bandwidth, minimally or maximally. But you have to let it through. It has a separate reserved lane, reserved bandwidth. And if you have mission critical applications, for example storage, you might want to use this. And then it looks like this. This is an ordinary network where you don't use quality of service. Well, your fire brigade, your emergency services, they get stuck in the traffic jam, just like anybody else. So if you use data center bridging, you have a lane for your emergency service, or perhaps a lane for the bus, or carpooling lanes, whatever you're used in your country. But that's the parallel. This is a hardware thing, but it's also a network card thing. So your network card needs to support it, your switches need to support it, and your operating system needs to support it. So if anybody ever starts talking about the extensible switch, and they show this Cisco picture, it's very nice for the people who need it. But the extensible switch is also the capability of putting quality of services on your NIC, on your hosts of your virtualization cluster. Which means, if you have those 4 NIC ports in one big team, you can use this for quality of service and make sure that every type of traffic gets the amount of bandwidth it needs. And you can make it as fault tolerant as you want, because you can go to 32 NICs And I can't even find a server to nick cards in. So that's not a very nice improvement. It needs quite a lot of, let's say, support for protocols and for specifications. They're listed here. Some of them are mandatory, and some of them are just enhancements or optimizations. IPSec task offload. This is also possible now to the virtual machine. It's also very good for people. Why? A lot of people need to use it, but it puts an enormous overhead on the CPU. And if you're in a business that is required or needs to encrypt data, this might stop you from actually virtualizing those servers or those applications.
How much CPU load does it actually generate?
20%. It depends, of course.
20% of one core, or 20%?
20% of let's say that if you have a CPU load and you should reserve 20% of your CPU for IPSec if you have a lot of traffic flowing over those servers. Of course, if it's a web server and you use IPSec on a web server and it gets 8 hits a day, don't bother. But if this is a database or a real-time application that monitors data, you're in the defense industry, you're in a regulated industry like financial transactions, then everything you do, not only your authentication, but also the package themselves, the transport is encrypted. And then it's 20% of your processor. Now 20% for a hardware machine, you might say, hey, just throw some extra CPU power against it and I'm happy, which is very fine in a hardware world. But when you're virtualizing, 20% taken away, like that, from the processor in your host, it's a big deal. So for those reasons, it wasn't always possible to virtualize every application or every appliance or whatever that needed IPSec. Now you can, because you can now offload your IPSec to the hardware card. So the IPSec offloading is not only for hardware anymore today, it's for all your virtual machines, and it gets offloaded to the network card. So the CPU of the host and also the virtual CPUs by extension don't have to deal with it. Consistent device naming. People who rack servers and install them from scratch might like this. HP, Dell, they all support it now. They have a table in BIOS, and they actually store the name that they've printed on the chassis into that table. So what Windows shows now is correct. You don't have to start unplugging the cables to find out.
This is good.
It's a silly little thing, but it's like, wow.
We don't have local Ethernet connection, 1, 2.
Yeah. And actually, the first thing we thought about is why don't you use colors? Because if you use colors, you might use an LED, and you might store what color you have in the BIOS. Everybody was asking, why don't we make the BIOS writable, right? If I rename it to something, it gets written to the BIOS, which would be nice, of course, but of course it doesn't change. It doesn't change on the printed chassis. So it's a bit of a. But that was the first question a lot of people asked. Hey, does it also store the names I give it? No, not yet anyway. And then there's network virtualization, which is actually a huge topic because everybody wants it. Everybody's working on it. Everybody is going into open flow consortiums to build it, but they have it now. You can now do multi-tenancy in a secure way. You can isolate traffic. You can put 2 companies on the same physical infrastructure, and you can pass your security audit, which something is you couldn't do that before because you were all using VLANs, and VLANs per definition are not meant for security. Some people think they can provide security, but they can't. So if you tell that to a security auditor, you're toast. So it's like, this is a wrong assumption, and you've built your security on a wrong assumption, forget it. You can't do that. If you want today, without network virtualization, put multiple tenants on the same virtual infrastructure, you will have to have multiple switches and separate physical cards to build the network for those tenants. Now you don't anymore. And that's the isolation part, which is, of course, very nice, especially if you want to do hosting or you want to build a cloud or whatever. But there's another thing. If you're building a cloud, or if you are hosting, every department internally or every customer that comes to you, they all use the same IP addresses. They all use 10.10 or 10.1 or 192.168, the private ranges. Well, it doesn't matter anymore. You can host 10 companies that use exactly the same IP range on the same physical infrastructure, the same switch, the same network cable, the same network card. You can just mix and match. And there's two ways to achieve this. One way is IP rewriting. This works today, this works now, and it works very well. And it's water performant. It's not top performance, but it's water performant. And it outperforms the other option at the moment. And I'll tell you later why. But basically what it does, it just matches in a table what is the client address and what is the provider address. So whatever, you see the red corporation, you see the blue corporation, they're using the exact name IP subnet. Well, it doesn't matter. IP rewriting with IP virtualization will just make a table and send it to the correct machines, depending on which company you belong to. Now, this takes a lot of IP addresses, because for every IP address you have from a client, you need another one. You need a provider address. It's a one-on-one match. So if you have a lot of client IP addresses, you need a lot of provider IP addresses. And therein lies the limitation. And there's a way around this, and that's using generic routing encapsulation, which you will find on most quality switches today. And that actually just uses a key. It uses a key to say, this is the blue company, and this is the red company. And all the mapping isn't necessary. You can just have one provider address for the blue company and another provider address for the red company. And then you just take a key, encapsulate the content with that key, and then, okay, that's it. It's a lot less traffic involved. And due to that, it's more performant. There's only one problem there. The network cards today don't support it. It breaks all offloading. So if you use this with a standard network card, every possible optimization you've gained over all those years to offload every little piece of processing to the network card and to alleviate all CPU on your host, it's dropped. And that's why actually today they're telling us, if you want it today and you want performance, use IP rewriting and deal with the TCP/IP, the IP address hassle, that you need a lot of provider addresses. But this is actually the way to go. So everybody's pushing the NIC vendors very hard. Come on guys, build NICs that support generic routing encapsulation and combined with the offloading features. So that's the future. Today it's IP rewriting. But it's quite nice. It's very nice. This is basically the picture for the encapsulation. You just say, I want this packet to go from this IP address to that IP address, and this traffic belongs to key 20, and key 20 is my blue company. And basically that's it. So that's why they can work with one generic provider address. They don't need the one-on-one mapping. So this is available in Windows 2012. It's pretty neat. I have two use cases for this. It's to collapse multiple networks within the same company, the internet-facing one, the DMZ, with the production network, with the research network, with the development network. There's no reason now for us anymore to have separate networks for those people. We can just build one infrastructure, put all our investment in 10 gigabit that we have for them, and use maximize the use of it. Because now we don't really saturate that 10 gigabit network, but we don't want to put our traffic on there. Now we can. So that's one use case. And that's not a provider. It's just internally with a company. Bandwidth management. Apart from the bandwidth management we've talked about with the quality of service for data center bridging and for unified networks, there's another one that's built on the virtual machine level. You can tell a virtual machine you can have X amount of bandwidth, minimally and maximally. So that means you can do quality of service on a virtual machine. And you can do SLAs. People who pay a bit more get a bit more bandwidth. Or if you're not into SLAs or internal billing, you have certain machines that really require more bandwidth, that are more bandwidth intensive. Perhaps you're virtualizing unified communications or VoIP. So perhaps you want to do that. So you can. And there's another little feature where you can combine with that, and that's virtual machine priorities. So you can actually say, these are my high priorities machines, and they get the resources first. They also start first. So you can even have a rule They need minimally that amount of bandwidth, and they are a high priority machine. That machine will always get what it wants. And if really all the resources are gone, the lowest priority machines, they will be told, you're out of luck. But that depends on your use case, whether this is useful for you. Yeah, this is just a picture where you set it. And then the HyperV Extensible switch. I've talked about the most important feature in there already for me, because I'm not really dealing with customers or employees that are needing this at the moment. But it's quite nice. What you can do is you can capture the traffic and integrate it with solutions from network vendors. And with capturing extensions, you can write reports. If you want reporting, what is going on my network, you have that today, but not in the HyperV virtual switch. That's a black box. You can't touch it. Now you can. And vendors are writing extensions for that. Hey, I want to reporting. What's happening on my network? Perhaps for billing, perhaps for quality assurance, but you can do that now. And those are their capture extensions. And IMON is one of the examples of the vendors that already have that. Then there's the Windows filter platform. This is great. Perhaps you want to do you want to write a firewall, or you want to write an appliance that protects you from malware. They can inspect packages, say, this is malicious content, out of here. So that could be done already on your network infrastructure. Again, not on that virtual switch. That was the black box. So that's in there. And then, oh yeah, the filtering extension is also nice. That's what Broadcom is doing. And they actually prevent denial of service attacks with that one. Yeah.
This third-party software,
yeah,
is it going to run in a VM and gets connected to the extendable switch, or is it going to run in the parent partition?
It can. It can run in virtual software. Most of the time it's just software. But it integrates with all the other solutions that you have.
So it doesn't, in the HyperV infrastructure, it doesn't touch the parent partition. It will run as a virtual machine.
You have to see it as extensions on a virtual switch that you can hook into. So that hooking into is software anyway. Whether you run that software in a physical box or within a virtual machine or on an appliance, it really doesn't matter as long as you can get to that virtual switch.
From that point of view, yes, but from the point of view of might put the
you want to know
the HyperV unstable, then
no,
it's an issue.
It doesn't install anything on the parent, if that's what you're asking. Could it make my hypervisor unstable? Yes. Everything you develop within a hypervisor, if you don't do it well, whether it's networking or storage, it's going to make your hypervisor or your cluster solution unstable. So, yes. Is there a possibility? But even if you write something that enhances storage in a hypervisor and you don't do it right, you might get a blue screen on the parent partition, on the host. So, yes, there's always a possibility for that. But the Cisco boys and some others are really heavily on board in this, and they kind of like it. I haven't worked in environments where they really demand it or need it, but I'm told that most hosters, cloud players, the ISPs, they just want this. They've been asking for this for a long, long time, and they're all quite happy with it. I've seen some people from Cisco, they're like, yeah, this is what we need, this is what we want. They're very happy. But in smaller environments where those concerns don't play, people are like, okay, cool. But then I tell them about the HyperV Extensible switch in the other manner. Hey, you can do the quality of service there if you want to combine with 4 ports on your NIC team, because that's also part of that extensible switch framework. So there's something in there for everyone. Some people have told me, this is only for the big boys. But no, not really. Even if you build one cluster with 6 nodes, perhaps, or even 3 nodes, if you can use all these optimizations and run twice the load or 50% more machines on there, why not?
I take it a bit further. Even on the smallest 2 nodes, the idea of having 2 10G, which gives me everything, less cabling, you know. I don't need to remember this is for the heartbeat, this is for this is for that. I remove all that shit. It's awesome.
Yeah, but you still, but don't forget that you have to configure it in the virtual switch.
Yeah.
So you still have to define your networks.
Fair enough.
But
But in terms of cabling,
in terms of cabling,
you
yeah.
know,
Yeah, yeah. But you need to do it intelligently. If you are now maxing out your 16 gigabit fiber channel HBAs and you have 4 of them in the machine, you might not want to combine it on a 4-port NIC team, right? But if you're just building a cluster for websites, and those websites, a couple of hundred virtual machines, and let's face it, most websites, they don't do anything. They're very low load. They don't have any overhead. So if you can build a cluster with 1 unit servers, you just have 2 10 gig NICs in there to create a team, so you have fault tolerance, and all the traffic is divided up there. And you don't need anything for it. It's all in the box. So you don't have to invest in special network cards, or in blade servers, or whatever. Just out of the box. Just have enough network cards you need, and the operating system. And you're golden. So I kind of like it. I kind of like it on all levels. For the small players, for the big players. I think this is the nicest thing about HyperV. Everybody rides along the effort to make it a cloudable operating system. So the big boys are happy, but I, as a smaller boy, am also very happy. Because now I can do a lot more with a lot less effort, or a lot cheaper, or whatever, or a combination of both. So I'm rather pleased with what I'm seeing in Server 2012. Oh yeah, the Cisco, this is almost mandatory if you do a presentation for Microsoft. So you don't need to watch it, but they want to see that Cisco thing on there. I think somebody who works with VMware should know why. This is something you guys could do, and they couldn't. So they love the slide, but it's just marketing actually. So I know I must have rushed this through. My clock started ticking too late, I think, so I don't know. What time is it? Hey, I'm actually right on schedule. So if anybody has a question, I'm here. If you think of a question later, I'll still be here.
Could you please explain everything you explained
again
in more detail? It's
most of the info was actually in your blogs already.
Yes, or it's coming in blogs, yeah. And they will become more detailed on my blog. The moment I start working with it, but at the moment I'm pressed for time. I have something else very nice to play with now. It's my new stand with ODX, data transfer, offload, then provisioning up into the hypervisor without having to use sdelete anymore or run agents, all that cool stuff. So that should be delivered within a couple of months. So I have to divide my time between 2 very interesting subjects and keep the company running or something.
Like 2 months ago, I was giving a presentation, and some of the info I got it from your blogs, but I kept on doing some other research. The latency of fiber channel,
Yes.
and the latency of 10G
Yes.
with the SR-IOV,
Yeah.
and the latency of InfiniBand is getting very, very close. So the idea of iSCSI, or the normal TCP/IP network, is underperforming.
Yeah.
Between InfiniBand is like 3 milliseconds kernel to kernel, and iSCSI over 10G with SR-IOV is like 5 milliseconds,
But that's,
kernel to kernel.
so that's the inherent weak point of iSCSI. The latency of iSCSI is its biggest drawback, and it's because it has to go through the TCP/IP stack.
Yes, but
And
now
fiber channel is 100% offloaded to the HBA, and that's still the main big advantage of. But now,
my idea is this: as soon as 2012 is out,
yeah,
people start switching to 10G. 10G within a year is going to be half the price of what it is today.
Yeah.
At that stage, fiber channel is going to be expensive.
yes,
That is my prediction.
Yes.
Maybe I'm wrong, okay?
No.
InfiniBand is already half the price of the 10G. Basically, it's the same price, but you get a 40 gig, a quad rate.
Yeah.
You know, so...
basically, with RDMA, I would never go to InfiniBand unless I really, really, really need it. Because if you look at the price of a 10 gig RDMA card, there's not too many around yet. We're working on that, but there are a couple. I don't know them by heart. But if you can already get to 2.2, 2.1, 2 gigabytes per second, okay, that's if you have the storage to handle that amount of throughput, of course. That's theoretical, but
the problem, there's one small issue, but for literally, I was sending the quotes. I have a project which is going to close next week. The customer is not going to go for 2012. It's available beta, you know. So for this project, the customer is going for InfiniBand. However, end of this year or mid next year, because people will not switch to 2012 from day one, in most cases, we have running it in our labs, yes, but in production we're not going to have 2012, you know. So
100% from day one.
So eventually, yes. But so now there is a case for InfiniBand.
But basically what this is doing is actually opening the gateway for the next 10 years.
Yes, of course.
This is all overperforming for most people. But if you see what's coming at us in storage performance, in number of CPUs, and the quantity of memory in one host, I mean, I think Windows Server 2012 supports 640 cores right now. 640. I mean, you can put up to 2 terabytes in a single host. And that's today. What about next year? What about within 2 years? And they're like, you know what, we want to be ready for this one. This is one of the reasons why they put so much effort into the networking, but also into the storage. Actually, it's the same discussion with if you have a bottleneck. You take one bottleneck away, you just hit the other one. Okay. And you have to keep, and what they did actually is they went through the entire stack. The host, the NICs, the network. What is available? What can we use? What do we need to improve? But they did this for networking. They did this for storage. They did this for CPU. They did this for memory with NUMA awareness. It's all the way through the entire Windows host, up to the hardware. Where do we have bottlenecks and how do we take them away? And it's quite impressive to see what's possible. I'm not saying we are going to get those results because they're just trying to prove what it can do. Nobody is going to put Fusion I/O cards in their servers just to prove, hey, look how fast my NIC can go. I mean, you need a business case, well, most of us do. But it just gives you the potential. You know, if I use it today, I will not be running into problems next year or within 2 years. This thing is good for a couple of years, and then they build something better. So, frankly, I'm quite excited about Windows Server 2012. It looks very promising. My biggest problem is buying the hardware right now to play with it, because half of it isn't commercially available. And it costs money. That's